All right, recording is rolling. It is Tuesday, October 11th. Come back from a 3-day weekend. Okay. And last time I saw you guys, so this was last week, we were starting the rotational motion. You guys did a lab to solve for centripetal force. And where we're going with this is I need to eventually get you guys some universal gravitation notes. Then we're going to put those ideas together, like rotational plus actual gravitation, and solve for orbits. Right? How fast you have to go to keep the satellite in orbit. So that's where the story's going. All right, so let's look here. Top scientist for your dynamics quiz. So yeah, if you're on this list, then awesome job. You guys did great. This is back in your folders that I've had in over the weekend. You guys know that we just finished the first quarter. So yeah, there you go. You're on that list. Way to go. So this is going to be a weird week. Obviously, we weren't at school yesterday. I'm not going to see you guys tomorrow. So tomorrow, there's a PSAT. Yeah, and so you guys are going to be in the cafeteria. All right, so I'm going to tell you a little bit later in class what I'm going to have you guys do tomorrow, but you guys do have this cardstock page of this nice thick paper. So hold on to that. There. All right, because it's going to tie into some stuff that we did last week and also the starter question here. So this is a good review question to bridge us back from last week. First of all, last week you saw one of these, this O'Neill cylinder, right? I think it played you guys some video clips, showed you guys some artist renditions. Basically, if you have a giant cylinder in space and you give this thing a spin, okay, if you're standing on the inside, well, what's going to happen? You guys know from Newton's first law of motion, you only ever want to move in straight lines. If you took the walls away, you just like, here, this thing is going this way, right? If you took the walls away, this guy would fly off tangent to its motion, his motion. But there's this wall underneath him providing this normal force, okay? And so he's going to perceive this as sort of like a gravity field. Now, it's not an actual gravity field, right? It's like fake gravity. That's why I put G sub artificial, right? But if you know how big this thing is, and you know your target gravity, which is the two numbers I gave you right here. So last week we gave you guys some different numbers, but suppose you have a nice big one. We got look at this. So if you have 1 kilometer diameter, 1 kilometer, that's 1,000 meters diameter, right? Wouldn't there be a radius of 500 meters? That's where that number comes from. So 500 meters radius, okay? And hey, let's have a target artificial gravity of exactly here at the surface of Earth. That correlates to some exact spin rate, which the more technical physics term for is angular velocity, which we've been designating this, looks like a curly W, that's Greek letter omega, okay? So that's the question is, well, how fast do you have to get this thing rotating, right? So let's, let's see that. Okay. One more thing, right before we do that, I know I gave you guys your homework assignment a little while back. Let me flash this up here again. You guys have seen this before, right? So you guys know Wikipedia Classroom, Unit 3 progress check has been open for a while. I do have the due date is this coming Monday. I may bump that as we get closer, but for now, here, at least that's open. You guys can go in there, look at that. Right. And then, I gave you guys these chapter 7 problems. Right. They look like this. You guys have had this paper for a while now. So I do have to bump this date because, we just have like such wacky schedules going on. If you don't have that page, then here, I've got a couple extra copies on this desk right here. If you didn't get that for whatever reason. Okay. All right. So you guys got that? Okay. And then, as always, I put like twice as many problems on there as I'm actually assigning. So if you want extra practice, okay, you guys know that all the solutions are posted on Google Classroom, again, as we've been doing all along this class. Okay. All right, so you guys get that? Okay. All right, so let's figure out the answer to this question. Right? Maybe it's kind of a two-part question. First of all, you have to figure out how fast it has to spin. Okay, and then you can answer this question more directly. Okay, so you guys see a poster up there? See 3 new posters? Right, the one on the far left is probably going to help you out the most. Okay, so I'll tell you what to do for anybody watching this video. Here's what these are, and we went over these back on last time I saw you guys. Okay, so we're starting to think about how things rotate, and there's this new kinematic type motion. It's just for like rotating discs. Okay, some of you guys have these turntables at your desks. Okay, this is review from last time, but it's been a long weekend. Okay, so like these three Roosevelts right here, they all have different linear velocities. If I point a radar gun on, this guy's going to read 0 meters per second, and then like some speed and twice that speed, right? Okay. But in terms of angular velocity, like turns per time, they all have the same, right? And that's what this Greek letter omega is, right? In radians per second, okay? So we got radians, like how far you turn, okay? And I really care about radians and not degrees or revolutions, because radians, if you put the number of radians directly into equations, if you feed them directly into equations, they'll naturally, it'll naturally grow. I couldn't put some number of degrees and get how far it's turned in x, right? Like in meters. But this point is move some distance x. So this page connects how far it's moved linearly to how far it's rotated, right? I guess that's right. All you do very simply is just multiply by this distance r. Now you can translate back and forth between your angular values. Some do like how far it's spun or how fast it's spinning, right? And how far it's moved and how fast it's moving. Okay, so you guys got that connection. Okay, I told you guys that you guys remember those three kinematic formulas that we used over and over and over, right? These three guys. If you just substitute in the rotational equivalents, you get three completely new valid kinematic equations. Now time is still time, but instead of x, now it's theta. Instead of v, now it's omega, right? And so now you can get something about rotation. You can solve these. And so this is going to come back in later today. Okay. Okay. And then this one right here might be most helpful for figuring out this O'Neill cylinder thing. This top formula here, you guys pieced together, you guys figured out empirically with a lab, this last lab you guys did, right? The centripetal force, right? The force that's allowing something to stay in a circle is mv squared over r. The mass of this bob times its linear speed, v, square that, divide by radius of curvature. Okay? Now remember, centripetal force is never a force unto itself. It's always provided by one of the classic forces, or sometimes a net force, right? So it might be a tension in a string, it might be a normal force from the wall, in case of an O'Neill cylinder. It might be gravitational force in case of a satellite, right? Or it might be like a net force if there's like several forces acting to add or subtract them. Okay? But then to get a step closer, if you have like a solid moving disk, like a rigid disk, like those turntables on your desk, it might be more helpful to I showed you guys how to go from here to here just with the substitution last class. So if you know how fast it's spinning, right, this mass, that point mass times the spin rate, the angular velocity squared, multiplied by the radial size, right? All right, so let's adjust this last formula one way, which is if you divide both sides by mass, m, right, then this is no longer a force. Guys, force divided by mass is equal to what? Acceleration, right? Acceleration. So can I say acceleration is omega squared times r? Right? All right, let's go back here. Okay. Got you guys to do this one just to save some time, but this is definitely a skill that you guys should be able to do. Okay. So I'm looking at this O'Neill cylinder, right? I'm thinking about all these people standing at the edge, and I'm thinking this right here. The centripetal acceleration they experience, which is caused by the normal force from the wall on them, so that's where the force is coming from. Okay. Right, but mathematically it's equivalent to the rotational rate of this, the angular velocity squared, multiplied by the radial distance from the center, right? Okay. You guys see that? Okay, isn't that just a step away from this guy right here? All right, you guys good so far? All right. All right, so see, we're solving. Let's solve for this guy because we know these two guys, right? Like, what is this number right here? Yeah, 9.8 meters per second squared. I mean, acceleration is going to be meters per second squared, right? Okay. So, yeah, look for a number that has those units. 9.8 meters per second squared. Remember, we're trying to create some artificial gravity, right? If this thing's spinning too fast, it's going to feel really heavy. If it's not spinning at all, it'll just be put around in space. Because right? It'll spin at just the right rate. Okay? And we're trying to figure out how fast does that have to rotate. Okay? And what number goes right here? 500. Yeah, 500 meters. There you go. 500 meters, right? 500 meters. Right? Can you guys do a little algebra and solve for how fast it's rotating? And divide this 500 down, take the square root. All right. All right, you guys getting that number right there? All right, you guys getting that? You guys beat me to this answer, right? Okay. And guys, that number is not just a naked number. It has some units on it. What's the units attached to this number? Bam! Radians per second, right? Remember I tell you guys like radians is the best like way mathematically to define like so how far you turn, right? And here's why, right? Because it naturally falls out of the math, right? This didn't tell me anything about degrees or revolutions, radians, like radians per second. Okay. Okay. All right. Now we're definitely a step closer to answering this question. How much time does it take to go around once? Right? You had to do that first. Oh yeah, go ahead.
Where did you get the equation from?
This equation, right? Well, it came from your lab, right? So in your lab with the Plato canisters and the PVC pipe, you guys got this, right? Right? MV squared over R. Then what I did was I said, well, I know that this V is equal to omega times R, right? V is like a linear speed, right? Like if I point my radar down at any one of these Roosevelts, right? Where this guy's zero, this guy's medium fast, this guy's really fast, right? But they all have the same rotational rate, the same omega, right? Like turns per time, radians per second, right? And the connection between these two is this setup right here, this expression. So I can substitute omega R, I can put in place of the V. So that's exactly what I do right here. In place of this V, I put omega R. This is back in your notes from last time for Friday, right? And you can get this new expression, right? Then if you divide both sides by mass, this is centrifugal acceleration, and it's just omega squared times R. Okay, so there it is. Okay. There we go. All right. And so now we know how fast this thing is rotating. I don't suppose anybody's figured this out. Yeah, what you got?
44.8 seconds.
Bam! That's it. That's it right there. All right, glad you got it. Yeah, 44 point something seconds. That sounds right. Okay. So there's a couple ways you can go about this. You could use a modified kinematic equation. Like you guys remember x equals vt, right? Distance equals speed times time. You probably could have done that before you were put in this class, right? You can find the rotational equivalent of that. Now this is at zero acceleration, right? So acceleration is 0 meters per second squared, right? Okay. The rotational equivalent is theta equals omega t. Would that also be true, right? And if you know one revolution, guys, one revolution, how many radians is that?
2 pi.
2 pi. 2 pi radians. Okay. You know this number is 0.14 rad per second. That's just this right here. Okay. And times t. Okay. So divide that over. Okay. And I think back on Friday I solved this using dimensional analysis, so I used a different method, but it'll get you the same place, right? So now you guys got two ways: your notes from Friday and also what you're looking at right here. Take 2 pi radians, divide by 0.14 radians per second. Okay. And I'm getting a time of, yep, there it is, 44.87 seconds. Okay. About 45 seconds. Okay. Okay. So that's to say, if you had an O'Neill cylinder floating up in space with a diameter of 1 kilometer, and you wanted to spin it so that everybody on the inside thought that they were on Earth, right? It'd be really hard to tell the difference. Okay. There'd be a subtle Coriolis effect. Then, yeah, you'd want it to spin around once about every 45 seconds. There you go. Okay. Okay. You guys good there? All right. All right. So let's see. All right. Let me go ahead and give you guys your assignment for tomorrow. Assignment tomorrow. Right. So here's where this card slot comes in. Right. This thick paper. All right. Go ahead and take the ruler on your desk and give yourself a margin on the right side, about an inch, maybe 2.5 centimeters or so. It doesn't have to be exact, but give yourself a margin on the right side. Okay, guys, yeah. Okay. And write your name, somewhere on this page. Okay. Okay. Now, this is an activity I always do with my students, so tomorrow will be a perfect opportunity since I'm not going to see you guys. You guys are all going to be, where are you guys going to be tomorrow? Cafeteria, right? Good call, cafeteria. So tomorrow you guys are gonna be in the cafeteria. You have this page, and you guys are gonna get to use your imagination to design an O'Neill cylinder. Connect this again. 3209, connect. All right. All right, let's just present screen 2. All right, O'Neill cylinder. All right, so you guys remember? Here, let me show you one of the artist renditions of this thing. Could look kind of like this, right? So this is kind of what we're going for. Now, we're gonna create like a giant like class O'Neill cylinder sort of thing. I'm gonna hang it from the ceiling, right? So thing I've always done every year. Right? And every student gets to design a little part of it. So you might want to think to yourself, if I were engineering one of these O'Neill cylinders, what would be some good things to have on this thing, right? Might be kind of hard to maybe import, export resources. Maybe you want that in mind. Maybe all the things you need on Earth, right? Might have some kind of self-contained environment. You know, we're going to get water, food, energy. Okay. And see, the way we're doing this is we're doing an aerial view version of this. So we'll show you guys some past examples that have been pretty good past examples. Right. Yeah, so one looks like this. This is like an aerial view, right? Like you're looking down on this, right? Like you're looking down, right? Whoops, let's get past that. I got like this one here. Yeah, now you see how there's like this margin on the right side, right? Right, that's gonna come into play here in a few minutes. I'll show you guys what. Okay, so like looking down on this thing. It's like upside down one, but it's all right. Got the space place. Not really aerial view, but that's all right. Okay. Imagination, I think that's what matters. Okay. Right, here's let me show you guys what. Oh, actually, I got a trivia question for you guys. What city are you looking at right there? Yeah, it's like Manhattan, New York, right? Yeah. So here you go. Oh, here's a. Doesn't have this in my files too. Here's a more zoomed out version of this. Right. So more zoomed out version. Just to give you guys an idea of like aerial view if you're looking straight down. Imagine if you're building something like this in space, you want to make the best use of your land and resources. So it might be more dense than like suburban, but yeah, again, your imagination, you get to do what you want with it. Okay. So we switch back over here. Okay. Now how this is all gonna go together is you're going to have your own panel, right? Your class, it's got a margin on the right side, right? Your classmate has a panel, right? All your classmates have panels. Okay? You guys see how this is going to glue together like this? I'm just going to glue, right? Okay. And then from this, there's going to be like a giant strip, right? Where here's yours and your classmates and your friends and your teammates and everybody gets one, right? Okay. And then, you think we can wrap this together? A giant cylinder, just like that. Throw it on the ceiling. All right, and then maybe this could be like yours right here. Right? You guys got that? Okay. All right. Flip my screen over here. I just show you guys one example of sort of a final product on this.
Guys, look how you're.
Oh yeah, Griffin narration. All right, so then it comes together. All right, so you guys get on that? You know what you're doing tomorrow? All right, who's got any questions? All right, so let's get back to hard AP type stuff. All right, so, okay, yeah, before I forget to, one special thing for you guys. You guys remember this one-to-one device agreement? All right, so about 30 of you guys have turned this in. If you haven't yet, then have this out, and then before you walk out of class today, you can just pop this in the grade tray. Okay? The device agreement. Okay, that's just for you guys. The first period. All right. So this page right here. One more time. Who does not have the page? Does not have this page? Oh, no, there's one. All right. Yeah, thank you. All right. So we're all good there. All right. So let's here. We're just gonna you guys can just follow along with me up here. If you want one of these turntables yourselves, looks like there's a couple of spare ones on these desks that got from math students today, or maybe you're lucky enough to have one yourself already on your desk. So I'm gonna give this thing a spin, and let's jot down some numbers, make some graphs that pertain to that type motion. Hey, look at that. That's what that looks like right there. Right? All right. So let's go left to right on this page. So it says let's think of 3 revolutions at constant angular velocity. Now I went ahead and filled in the top number for you. Maybe I shouldn't have done this, but you guys know that 1 revolution is 2 pi radians. You guys just told me that a few minutes ago. So wouldn't 3 revolutions be 6 pi radians? Right, you just triple it. Okay. Oh, let's take a look at what that looks like. Zoom out a little bit here. Okay. So if this is my x-axis 0, let's go 1, 2, 3, right? And that's approximately constant angular velocity. Well, if I just let it go, it looks like frictional force will slow it to a stop. Okay. All right. So how much time did that take? But let's sort of fudge the numbers. We'll just make something up. Could that have been maybe maybe what do you think? 5 seconds maybe? All right, let's go with 5 seconds. Let's see what happens. 5 seconds. Okay. Can you guys tell me if you know it went 6 pi radians? There it was 3 revolutions, what that equivalent to? Okay. And it took 5 seconds to turn those 3 revolutions or 6 pi radians. How fast it was rotating in radians per second? Can you guys do that? Okay. Okay. You figure it out. Yeah, go ahead.
Would it be 3.8?
All right. Yeah, Jack's got it. Like 3.8. Right, there you go. So you just do 6 pi radians divided by 5 seconds. Get like this number. Okay. There we go. Right. Oh yeah, no, that would be correct to 2 significant figures if you had 2 sig figs, right? So yeah, 3.8 radians per second. Right. Then release and allow it to slow to a stop. Well, here, let's take a look at this. Okay. Was doing. Okay. Try to repeat what I just did. All right, 1, 2, 3, and then just let it slow to a stop. Right. Looks like it slows to a stop right about there. Okay, let's treat that as a thing, right? Now we can pull up a protractor and figure out how many degrees that is. We convert that to radians. Okay. So here's 0 degrees right here. That looks about 150. Maybe we'll call it 150 degrees. 150 degrees, I think. 150 degrees. Okay. All right, so 150 degrees it's slowed to a stop. Okay. Now how many radians would that be? Oh, I think I could solve this with dimensional analysis, right? Give you a little conversion right here. So you got what?
6 over 5
Six-
radians.
6 over 5 radians? All right, check this out. 150 degrees. And I don't know that every I know that every 360 degrees is 2 pi radians, right? Or if you like, you could have done pi over 180, right? A lot of students like to do that. Actually, I like to do that too. Pi over 180, it's the same ratio, right? Okay. Let's see what this is. Well, it's 150 times 2 pi divided by 360. I'm looking at 2.62 radians. Right now, that's probably too much precision, but right. You guys getting that too? Did that right? Right. So back over here. Okay. Right. Once I released the external force, so it stopped going at a constant angular velocity, it just slowed to a stop. It did that in 2.6 about radians, right? And the time, yeah, let's just let's fudge this. Let's say it took about I don't know, a second, okay, 1.0 seconds. Okay. Okay. All right, you guys get that? Because that's probably pretty close. All right. Now, I don't know why I did omega average. We'll come back to that one. But let's definitely figure out what is the alpha. Isn't that the rate that it's slowing down, rotating? Right? Can we use a kinematic formula, do you guys think? Like, do you guys remember V final equals V initial plus AT? You guys remember that? Okay. Can I say that omega final equals omega initial plus alpha T? Right? Because I think we have enough information to solve that. Okay. The question is, what rate was it slowing down? Okay. And if it slows to a stop, then what is this number? 0 radians per second, right? What number goes right here? Initial angular velocity. Right? Wasn't that how fast it was spinning? Right at the moment I let it go. It was going this constant for a few seconds, then I let it go, but it was going that fast, right? So it's coming from 3.8 radians per second. Or if you want to say like 3.76, keep an extra digit in there for your little calculations, probably a good idea. Okay. Now alpha, I'm hoping it's going to be negative because it's slowing down. And this all happened in what, 1 second, we're calling it? 1 second it took to go from this to this. 1 second. Is that true? Okay. Maybe I should have made up a different number, but you guys get the idea. Subtract this over, divide by 1 second. Wouldn't alpha be negative 3.8? And guys, negative 3.8 what? What's the unit? Radians per second squared, right? Because radians per second, subtract it over, then divide by the seconds. Right. Also, it's an acceleration. So yeah, radians per second squared, right? And so that number is going to go, looks like I gave you guys the negative sign. Okay. So 3.8 radians per second squared. So just stop. Okay. Good so far? All right. Then I set up some graphs for you guys. Some graphs. Now, the left 3 graphs are, look at that. Displacement, velocity, and acceleration, but they're all angular values. So we got theta versus t, omega versus t, alpha versus t. And then the 3 on the right are your classic x versus t, b versus t, a versus t that you guys have seen like so many times in the class, right? Right. Oh, and I gave you guys a time on here. So it looks like what's going on is before this little time arc, this was the constant angular velocity section. And then at that time arc, that's where I released the external force and let it slow to a stop. Let's do what we usually do, which is start with the velocity versus time. This is going to be angular velocity versus time. This is your omega versus t. Omega versus t. In case you're watching the video at home, looks like that. Okay. So wouldn't this axis be omega in radians per second? And this axis is time in seconds? That's true, right? We got 0, 0 right here. Okay. So during the first interval of time, or tell you what, can you guys draw this graph before I do? Better yet, if you have pencil, right? So just in case you missed it, you can erase it and then redraw it, right? Right. Let's do this. Okay. For the story that we just did, Right, so what I'm thinking, hopefully you guys have by now, is that this was going at a pretty constant 3.8 radians per second for a few seconds. Okay. And then at this time, which was like 5 seconds later, I let it go. And then after 1 second, it pretty quickly went to 0. Right. Might change these numbers later so that doesn't look so steep. It took 5 seconds of right, and then followed by 1 second. Okay. Right. Guys good? All right. How about guys good? How about the top graph, theta versus t? So the vertical axis is theta, that's going to be in radians. The horizontal axis is time in seconds. Right? Okay. So, again, can you guys draw that before I do? Okay. So I'm thinking at time 0, it hadn't moved anywhere yet. So that point's on the board. Okay. And then didn't it pick up angular displacement at a constant rate? Okay. Guys, what is the slope of that line? 3.8 radians per second. Okay. And the slope of this line, 3.8 radians per second. Okay. And then right at the moment I let it go, which is this hash mark right here, I let it go. Okay. Did it still continue to move in the positive direction? Yes, it did, right? No, it was accelerating in the negative direction, but it was still moving. Okay. The whole time it was moving counterclockwise, right? Let me just again. So here's what you guys just saw. Okay. It took about 5 seconds to go around 3 times. 2, 3, and then I let it go, and then it just naturally stopped right about there-ish, right? Right. But it was always moving counterclockwise. It was always like gaining displacement. So is this graph going to continue to rise after you release it? Yeah, it's just gonna like hook down and slow to a stop like this. It's gonna be like look like an upside down parabola, right? It's gonna be smooth transition too, right? I should love these graphs that bigger. This right. So it's like a straight line. Followed by like an upside down parabola type with the vertex is like right at the top right there. Right? It's like slows to a stop. Is that okay? Okay. How about alpha versus t? So this axis is angular acceleration and radians per second squared. Here's your time in seconds. Okay. Now, again, see if you can beat me to the solution. Okay. During the first interval of time, the first 5 seconds, when it was going at constant angular velocity, what would acceleration be for a constant velocity? Yeah, 0, right? Everybody said 0, right? There's no acceleration. Okay. I sort of gave you a hint by giving you guys a big old quadrant 4 in this graph that should help you frame the problem. Okay. Because as soon as you let it go, frictional forces take over and cause it to accelerate at some negative value. Okay. Oh, in fact, what is that negative value? Yeah, negative 3.8 radians per second squared, right? Yeah, I'm definitely going to change these numbers for later classes so the number 3.8 doesn't show up all over the place because these are totally different concepts, right? The 1 second time interval. Okay. This is negative 3.8 radians per second squared. That's what that is. Okay. So that's what that graph will look like. You're allowed to jump it down just like that, or just do a very steep connection. So either way. Okay. So 5 seconds and then 1 second of that. And then it stopped. Right? Right, you guys good? All right, good so far? All right, let's go back and fill in this box that I skipped here. It says, what is omega average? All right, so let's just consider the part where it's just slowing to a stop. Just that 1 second where it's slowing to a stop. So I'm just looking at this part right here, that very steep fall down. Okay. Now guys, if it was going at 3.8 radians per second, it slows down at a constant rate to 0 radians per second. Do you think the average would be like half of 3.8? Like 3.8 over 2? See what that is. Like 1.9 radians per second. Okay. I'm going to put that in here. 1.9 radians per second. Okay. That's a good trick. Is whenever something is like slowing to a stop or starting from rest, like where one of the velocities is 0, right? Then if you look at the average velocity, during some accelerating interval, right? Then yeah, it's just like half of, in this case, half of the initial velocity, but if it starts from rest, it'd be half of the final velocity. Okay, guess that. Okay. So if you did that average velocity times the time of 1 second, that would also tell you how far it rotated. Is that okay? Here, let me prove that to you guys. If you do average velocity times time, so 1.9 times 1, that's obviously 1.9, right? That would be radians, 1.9 radians it would have turned, 1.9 radians. Or you could take the area under this curve, which is a very skinny triangle. You guys see that very skinny triangle there? Right, 1/2 base height. It is 1/2 times the base of 1 second times the height of 3.8 radians per second. So that's still 1.9 radians. Right? The area of this triangle is 1.9 radians. Or if you just did like the average 1.9 radians per second for 1 second, it would also get you a movement of 1.9 radians. Okay, is that okay? All right. Now let's go address the linear motion component of this. And so everything we've done so far is like angular motion, right? Something to do with like rotating. Right? But I'm looking at these 3 Roosevelts here, right? And I'm saying if I point a radar gun at these guys, that radar gun's going to read different values, right? 0 obviously for the middle, right? And then faster the further you go out. Hey, is the guy on the very outside moving twice as fast as the guy here? Like when it's in motion, is this guy moving twice as fast as this guy in a linear sense? Okay. I think so, and I can back that up with this right here, because everybody has the same omega, right? Or don't they all have the same turns per time? So if you double your radius from center, say you go from 7 to 14 centimeters from the center, wouldn't you also be doubling that effectively? Right. All right. So we got that. Okay. Let me get a measurement. Yeah, I'm looking at 14 centimeters for this guy on the outside. Let's follow up that guy's journey. Right, just the guy on the very outside. That's 14 centimeters away. Okay, so back over to this page. What's the radius? I'm going to do 14 centimeters. Okay, and then let's go answer a bunch of linear kinematic questions. Okay, so this is your traditional kinematic that you guys have seen since August in this class. Okay, So, oh, and I gave you guys all the conversions right here. To tell you what, if I could make any modification, because this is just basically your notes from Friday that I reviewed at the top of class today. Okay. Guess the one that says alpha is omega over t. I'd really like to change that to delta omega over delta t, right? Change in angular velocity over change in time, because you need a change in angular velocity to have an angular acceleration, right? Okay. So here, let me write it kind of big up here. Okay. So the one I'd modify a little bit is I'd say this: alpha equals change in omega over the time interval. Okay. Okay. But otherwise, it's just your notes. Okay. So this question: how far did that coin move during those first 3 revolutions, or 6 pi radians? Okay. Well, can you just say how far something's moved? Linearly, distance in the linear sense is how far it's rotated times its distance from the center. Right, you guys can do that, right? Okay. So let's do, this was your 6 pi radians. Here's your 14 centimeters, right? If you like, you can think about this 14 centimeters per radius and see if the radius would cancel out. Radius is one of those tricky units where, you know, sometimes it can like pop up or disappear. You know, it has this really tricky way of like canceling out. Normally your units are pretty straightforward. You know, you multiply or divide stuff, and then you just stay around. Yeah, radians can be a tricky one to keep track of. But I'm going to go 6 pi times 14, and the number I'm getting is 264. Okay. And that would be just centimeters, just plain centimeters. That's the distance x that coin went during the first 3 revolutions. Okay, is that all right? 6 pi radians times 14 centimeters. Okay, I could say it went 264 centimeters. Okay, it's a pretty good distance, right? That's like a little over 2.5 meter sticks. That's pretty good. Okay, let me ask you guys a different question. For the first 3 revolutions, what was the displacement of the outside point? 0, right? 0, because it ended exactly where it started, right? So the displacement would be 0, but the distance is 264 centimeters. Is that okay? Okay. Okay. Next question. Velocity, like centimeters per second. So if you point your radar gun at the outside point, can you just say, well, how fast is it rotating times the radial distance from the center? Does it give you that number? I think so. Let's do that. So V equals omega times R. So we're going to go 3.8 radians per second and a radius of 14 centimeters or centimeters per radius, right? I'm getting 53, that'd be centimeters per second. 53 centimeters per second. Okay. Gonna go right here. Right. All right. Okay. The distance to come to a stop. Well, I know how far it turned to come to stop. It was like 2.6 radians. Right? Remember, here, just remember, every radian's about 57 degrees, right? So about 2.5 of those. Okay? But you guys saw it was like 150 degrees is where we started. Okay? 2.6 radians. And it was 14 centimeters away. Can I just multiply those 2 together and get the stopping distance? Oh, yeah, go ahead.
For the distance, could you use the circumference of the circle?
Yeah, it is related to that, right? Right, circumference of a circle. So I did use this as the measuring tool in degrees, and we converted that to radians. I'm trying to shuffle everything into radians. If you did something to do with circumference, you could definitely do that. You guys remember this top formula even has that connection to circumference that you guys have known since elementary school. Circumference equals 2 pi r. Circumference equals 2 pi r is a very specific version of this more general equation, right? This general equation can handle any motion. Circumference is just exactly 1 trip around, which is 2 pi radians. Okay. All right. So yeah, I'm sure. Just like usual, there are usually like multiple ways to get to a solution here. Yeah. And so I'm gonna say the stopping distance x. Just gonna do exactly what I did here, right? Except it's a different term, about different angular displacement. So x equals theta r. Again, we're back to that. We're going 2.6 radians, and it was 14 centimeters per radius. What's 2.6 times 14? I'm looking at 36.4, but maybe we could just say 36 to two significant figures, right? 36 centimeters, right? 36 centimeters. Okay. Right. So 36. Let's see if that kind of makes sense, right? Because I do like to always connect the math back to like the physical world. You know, does this look like it makes sense? Okay. Remember, I spun around 3 times, then let it go, and it went from here to about here, didn't it? So that about 150 degrees. And I'm saying that this coin, this Roosevelt right here, which is 14 centimeters from the center, should have moved about 36 centimeters. Does that look right? 36 centimeters. Isn't that a little bit more than one ruler? A little bit more than one ruler? Let's see. Okay, so this ruler, if I wrap it around, oh yeah, it kind of runs out a little bit short, right? So yeah, it only runs out by a few more centimeters it would need. I go from here, is start wrapping this around. Yeah, it doesn't quite make it to the stopping point, which was about just a few more centimeters. So yeah, that definitely looks believable. This 36 centimeters distance that it would have gone. Okay. All right, and then these guys down here. All right, average velocity. Well, can I just take the angular velocity multiplied by radius of 14 centimeters, get centimeters per second? Okay. So what is 1.9 times 14? Looking at 26.6, maybe I'll round that to 27 centimeters per second. And then angular acceleration. Can I just take the angular acceleration multiplied by radius and get the linear acceleration, I should say? Okay. This would be, this last number we're about to fill in right here is sort of analogous to if you're in a car going around on a circular racetrack and you slam on the brakes and you're watching your speedometer needle go, say, what's the rate that your speedometer needle is moving down to 0, right? That's like what this is, right? Right. And so how to get it though is just, here, it's just this right here, because we know this number, we're gonna do negative 3.8 times 14. So what is negative 3.8 times 14? Negative 53.2. So negative 53 centimeters per second squared. Okay. Is that right? Okay, that's it. Okay, finally, let's knock out these last 3 graphs here. X versus T, V versus T, A versus T. Okay, this is some of the very first stuff that we ever did in this class. We're going to connect it back to that. Okay. Okay. So here I can play out these numbers. So I know that during the first, this was X in centimeters. This is time in seconds. During the first 5 seconds, it went 264 centimeters. 264. Except right there. Okay. And then during the last second, I'm going to exaggerate this last second a little bit, just to give myself a little more graph space. Okay, it went in only another 36 centimeters. Huh? What is 264 plus 36? Is that right? Yeah. Well, that's exactly 300 because that's interesting. Okay. So my graph isn't exactly to scale, but you guys get the idea. After one more second, it would have gone up to 300. And the only way for it to do that is it has to kind of curve down like this. Hey, does this graph look the same shape as this graph? Right? Now, of course, there are different units on the vertical axis, but I bet just in terms of the shape, I bet you could like warp them and put them right on top of each other, right? Okay. You think it's going to be the same story for the next 2 graphs? Ooh, I think so too. Okay, because it was going at constant velocity of 53 meters per second. Or I should say constant speed. That's what I should say, because it's going around a circle. It's constant speed at 53. This would be in centimeters per second. So centimeters per second. It was doing that for a while. And then during the last second, it slowed down to 0 centimeters per second. Time in seconds, right. Time in seconds, then acceleration in centimeters per second squared. Okay. And then this was negative 53 right here. So it had 0 acceleration while it was, okay, and here's the weird thing. Okay, guys, while it was going around at constant speed, right, constant angular velocity, there was an acceleration, but it was a centripetal acceleration. Notice I'm not saying anything about centripetal acceleration anywhere on this page. You guys know centripetal acceleration and angular acceleration are totally different concepts, right? From linear acceleration. Okay? Here we're looking at linear acceleration. in the sense of just it being on a straight line path. Like if you look at this, but if this guy was a race car driver, okay, okay, it's gonna be the same shape. Okay. All right, so yeah, all right, I'll see you guys in a couple of days. So you guys are gonna be in the cafeteria tomorrow, working on your O'Neill cylinder panels, and yeah, see you guys Thursday.